I tried to create a 3D scanning system using an ultrasonic sensor. The goal was to create a rough 3D point map by sweeping through different angles and combining the returns. But after enough iteration, I realized that there were fundamental issues in my system. Therefore, I started to model the system using linear algebra instead. Here's how the physical setup ended up. As you can see, it's an ultrasonic sensor mounted on two servos, and the ultrasonic sensor sweeps through the vertical angles and then shifts to the next arc. And it was pretty easy from there to combine all of that into a point map. And all I really was looking for from the point map was a fairly recognizable image of the object. Here's an example output that I thought I would receive. As you can see, the object is recognizable, but it's not a perfect image. And all of this seemed pretty reasonable to me. Here's how my 3D imaging actually turned out. I'm not going to put you through the pain of trying to guess what this object is, but it is the front face of a candle. We're looking at it from the top down view, so you can clearly see the curvature of the candle. Believe it or not, I was pretty proud of this image. And if I could show you guys the full 3D picture, it does have a nice front face, but it doesn't quite compare to the expected outcome. After this failure, I started to wonder if I could model the system using math to see just how possible it should have been. While the equations ended up being more of a idyllic geometric approximation, the stance I took on it was finding the simplest possible equation that I could solve and expanding from there. And you'll be able to see how adding these simple layers will get us closer and closer to a better representation of the physical system. If you can imagine a point in a 3D space that sits at the origin and shoots a cone along the x-axis towards an object, the first thing I did was check how many points on the object, that being a sphere, are illuminated by this cone. That is, what rays of the ultrasonic sensor are actually hitting the object. Next, which points are hitting the object too obliquely. Let's eliminate those points. After that, we create another point in space that can be our receiving terminal. So it needs to leave the trigger terminal, our initial point, and enter back into the receiving terminal. But we can't expect the ray to enter a single point. So let's apply the physical receiving aperture, which is a 1.5 centimeter disk. If the ray enters that disk, then that counts as a successful reception. Well, both terminals won't stay in the same position the whole time. If you can imagine the physical system, they both sit on the same board. So if we put a point in between the two and extend vectors outwards, we can instead rotate that line to then change the position of where the receiving terminal and the trigger terminal will sit in space. Everything I've described thus far has been purely geometric, but that alone isn't enough to decide whether a return actually makes it back to the receiver. Imagine zooming in on a tiny patch of the surface. Whether that patch produces a usable return depends on how smooth it is relative to the wavelength of sound. And for a specular reflection, the roughness actually matters a lot, which is what the ultrasonic sensor needs. A common way to model that is with the Rayleigh rough scattering formulation, which just takes the incidence angle, surface roughness, and wavelength, which is the equation I ended up using. So when you put all this together, what you get is a sequence of binary checks. And in practice, you would write out code to loop through different angles and see which points gave you the return values necessary. But I'm not going to do that because the math already answered the questions I cared about. Even before the implementation details, the geometry and physics alone guarantee large blind regions. Granted, a sphere is the absolute worst case scenario object to be scanning. I mean, some solutions to our system would be rotating the object, but the object would need to be rotated on multiple axes, and again, that would ruin the point of being able to interchange objects. We could use ultrasonic sensors, but we would need multiple independent viewpoints. If I had to try again, I would use LiDAR instead because we just avoid the specular return constraint entirely. But all of these fundamentally change the project. None are refinement, so that's the reason I stopped.